so now we're gonna be moving on to number 3, and in number 3 it's gonna be a differential. Okay, so well, I come back to calculus 1. Right? In calculus 1, if y equal fx, then dy equal f prime x dx. The differential is used to estimate the actual difference delta y. When there exists a delta x. Okay, so this is what we did in calculus 1. So in this class, well, we have z equal fxy, and then we're gonna cook up how to approximate delta z. So it means delta z here is gonna be a small change in x and y, right? So it's gonna be a fx naught plus delta x, y naught plus delta y, minus, well, fx naught, y naught. Yeah, just a little change in x and y gonna give you a and delta z. So we can actually approximate the f of x naught plus delta x, y naught plus delta y, because it is a point very near x naught, y naught, right? Well, we can use the tangent plane at x naught, y naught to do the approximation, exactly linear approximation. Okay, so linear approximation, right, mean that that is approximately equal to, right? Not exactly equal to, though, approximately equal to. Okay, so I'm gonna put this in here. Right? Fx naught plus delta x, y naught plus delta y is gonna be f x naught, y naught plus fx, right? X naught, y naught, because we use the tangent plane at x naught, y naught, so it could be f x naught, y naught. Okay, so the difference delta x, that is x minus x naught, right? Minus, no, it's not minus yet. Could have a fy x naught, y naught delta y minus f x naught, y naught. Yeah. Okay. So this equal to the fx naught, y naught going to cancel out. So which going to give us the fx x naught, y naught delta x plus fy x naught, y naught delta y. Yeah. And this is how we use partial derivative to estimate the actual difference delta z. So we know that delta z is going to be fx, that x naught, it's not going to be the approximately y naught. Instead of delta x, I'm going to use dx there. Plus fy x naught y naught dy, and this one is dz. So this is the formula for differential. Pretty cool, huh? Example, let z equal to x squared plus 3xy minus y squared. Evaluate dz if x changes from 2 to 2.05, y changes from 3 to 2.96, and then b compute the actual change delta z and compare to dz. Okay. First thing here that we need to do is that we have to compute the dz, and then we do the substitution correctly. Just got to evaluate dz here. So in A, so according to the formula, dz is the fx x naught y naught dx plus fy x naught y naught dy. So the value of x naught and y naught, and then the dx and the dy, according to here, should be able to do them. So in order to do this, right, I'm gonna have to do fx here first, and then just gonna do the substitution here. Fx is gonna be 2x plus 3y. That fx x naught y naught, they are the number that are 2 and 3. So 2, 3. Plug it in, say 4 plus 9 is going to be 13. Fy 3x minus 2y fy 2, 3. 6 minus 6 is going to be 0. Okay, so $13. Okay, what is the dx there? 2.05 minus 2. And then for the other one, it's going to be a negative number. Right? Just got to be careful with this thing here. It's the 2.96 minus 3. So 13 times 0.05. You multiply them, you're going to get a 0.65. So that is the dz. We're going to have to compute the actual change and see how it how they compare to each other. Are they going to be the same, not the same? Đấy. Can be, well, the actual change, right, is the delta z. So if it's the actual change, then you don't have to do the partial derivative because it is actual. So it's gonna be the function, right, f at the point. Well, you change it from 2 to 2.05, so you got to do 2.05, 2.96 minus f up to 3. Yeah. Okay, so this is the actual change. Yeah. Okay. Yeah, you got to use your calculator here because it does look pretty ugly though. 2.05 square plus 3 times 2.05, 2.96 minus 2.96 square minus 2 square plus 3 times 2 times 3 minus 3 square. Oh, 0.9449. Oh, 449. It should be a little near, I think. 0.449. Yeah, do a comparison, right? And DZ is pretty good, right? Use the picture here. This 10 centimeter. This one right here is the 25 centimeter. Assume both radius and height of the tank on the left side has max error. .1 centimeter. Number one, here come A. Estimate the max error in calculating the volume. Oh, volume. And then B. Well, this a little tricky here. Huh? If the height changes from so you can see where the max error come from. 25 centimeter to 25.1 centimeter, and the radius changes from ten centimeter to 10.1 centimeter. Is the volume more sensitive to a change in height or a change in radius? B is gonna give you some thought. So we know that volume is equal to 1/3 pi r square h, right? We want to do dv, so that's going to be a vr, right? dr plus vh dh. Yeah, right. Okay, so one of them is the sensitivity to change in radius, and then another one is the sensitivity to change in height. Okay. Partial derivative with respect to r is going to be a 2/3 pi r h times dr, and this one is going to be a 1/3 pi r square dh. Pi radius is 25, height is 10. dr, I'm gonna sub in the dr later. Just going to do b first. 1/3 pi 10 square dh, 500/3 pi dr, and then this one is going to be a 100/3 pi dh. So from here you can see that, oh man, it is more sensitive to a change in the radius, because look at the sensitivity here. The number in front of dr, it is sensitivity to change in radius, and then this one is sensitivity. Oh, so you know one more thing about the partial derivative. You can also use it as the sensitivity. Over 3 pi times dr is 0.1 100. So dv here is 20 pi. And according to this, then the volume is more sensitive to a change in radius. We know that the BMI of a person is the body mass index. I'm going to do F HW, and that is W over H squared. We know this formula. The only question here that I have for you guys is the BMI formula more sensitive to a change in H or W? This would be F H dH plus FW dW. Partial derivative with respect to H is going to be a -2 W over H to the power 3 dH plus 1 over H square dw. Well, if you can see through this, good for you. But if not, then we're gonna have to do another thing here. It is clearer if you do the percentage change. That is df over f. Df over f equal to -2 w over h3 dh times 1 over f. So h square over w plus 1 over h square dw times h square over w, because we multiply by 1 over f there. So what do we have? We have a df over f, and this is the -2 dh over h. This one is dw over w. And as you can see, if you look at the percentage change or relative change, yeah, the BMI score is more sensitive to a change in height. Yeah, pretty much this is it for today. Hopefully you learned something new and useful.